I've been involved in trying to build thinking machines and stuff for a while. Well, I first started doing machine learning at the University of Waikato in New Zealand using the Weka workbench. Some of you, if you do any machine learning, you may have seen it. It's pretty neat. It's free software, and it's got all the classifiers and so on all written in Java. And you can, there's a big GUI, and you can just plug and play with them all and just visualize it and everything. So it's pretty neat. So I started on that, and then I went. A number of years later, I started working with Ben Goertzel, which quite a few of you probably know. And I started working in New York on his project, Intelligenesis, which later became WebMind. And one of the things that struck me when I was working there, as we're all meant to be working on building a thinking machine, if I went around and I talked to different people in the offices, what are we trying to achieve? What is intelligence? They'd all give me different answers. And not only would they give me different answers, but some of their answers would actually contradict each other. I mean, they would actually be inconsistent with each other, is what I'm saying. And in any project where you can't actually agree on where you're trying to get to, the different people working on it, I think that's a bit of a problem. And so this got me interested in trying to understand, well, what is intelligence? Can we try to define more precisely where we want to get to? Now, if we can define where we want to get to, we might be able to come up with better plans on how we might try and get there. So, what I've found in general since then is that if you talk to different people in artificial intelligence, you get roughly 3 categories, I think, of answers about, or what is it, when you ask them, well, what is intelligence? One group of people basically give me answers along this line. They say, well, I'm not really working on intelligence. I do speech recognition, or I build classifiers, or I do whatever. And I'm not really sure what intelligence is. Now, I respect these people because I think they're honest. I think they genuinely don't know what intelligence is. Maybe they got interested in the field to start with because they wanted to do something like this, and then they started building classifiers and doing whatever they do. And they do define rigorously what it is they're trying to do. There are definite measures of the performance of say, categorization and so on, and they can, So it's quite a concrete thing. But they're drifted away. They're no longer trying to build a real intelligence. They're not even really sure what it is. Then there's another group of people, and I think it's summed up by something like this quote: "My reaction to intelligence is the same as my reaction to pornography. I can't define it, but I like it when I see it." And I think this group is the problematic group. Basically, their attitude seems to be, yeah, I don't know what intelligence is. I don't know where I'm trying to get to. But I think when I arrive, I'll know it. And so let's start writing some code and building some system and trying to make something that does some stuff. And we think intelligence has something to do with this and something to do with that. So we'll throw a bit of this and then throw a bit of that in. And we sort of meander around in different directions, and so I think that's really not a very productive. Well, yeah, you can discover some things along the way, but if you're really serious about getting somewhere, it's good to think seriously about where that is you want to get to start with, before you start trying to head off in different directions, and you're not even sure when you arrive there whether you've arrived or whatever. And it leads to all kinds of problems. One of the problems that you've probably heard about is this shifting goalposts. People will say, okay, playing chess, well, that was going to require real intelligence. Then it's sort of solved in a brute force way, and they're like, oh, maybe it doesn't really require intelligence after all. Playing Go, that's going to require intelligence. In the last few years, there's been an enormous amount of progress in Go playing systems. They can now compete with the low-level professional players. And so people start to think, well, maybe Go isn't really intelligence either. And I think that's a symptom of this problem of not actually having a clear idea where we want to get to, but thinking that, well, when we arrive, eventually for our random sort of search, we'll know it when we get there. So I'm in the third group, and I think it's summarized by this sort of quote. Basically, what we want to do is if we're serious about the I in AI, we've got to think seriously about what this thing is, what it is, what it isn't, and try to make it a bit more concrete. Or even just make it more explicit exactly what the different opinions are and so on. And almost nobody does this. Almost nobody does this. I published a paper. I put together the biggest collection of definitions of intelligence that, as far as I know, anyone's ever put together. I also put together the only, which I think is remarkable, the only review of measures of machine intelligence. You think about that. You got this whole field, artificial intelligence. Nobody has ever done a review of measures of machine intelligence. As far as I mean, please tell me if somebody else has done it before. As far as I know, nobody's ever done that. That's ridiculous. If you want to be a science, you need to define things and you need to be able to measure things. Otherwise, you don't even know if you're making progress. You don't even know where you're trying to get to.
So if anybody's looking for a topic for their thesis that they're writing, they can have a go at that?
Yeah, it's a difficult thing to work on because you tend to get ignored. The people in the area, a lot of them, are either this group, and they're like, oh yeah, we're not too worried about what intelligence is, but at least they're honest, they know they're not trying to do it. Or they're this group, and they're like, oh, we don't really care about defining intelligence, we're going to know when we get there. And so you're generally ignored. So my review of measures of machine intelligence, as far as I know, has never been cited by anybody in the last few years. People are just not interested in this, and I think that's fundamentally wrong if you want to be a scientist. So, but there are a few people that write papers that say, hey, we need to define it, and this is one example here. Right. So, what is intelligence? Now, I'm going to present this a little bit backwards in a way. I'm going to present my results first, and then I'm going to present some of the supporting evidence for it. And the reason for that is that it's easier to judge some of the supporting evidence if you already know where I arrived at the end. See? So it makes sense in that way. So what I did, as I said before, is I put together this big collection of definitions of intelligence from organizations, from psychologists, from artificial intelligence researchers. And I went through all these definitions, looking at the commonalities, and it seemed a bit discouraging to start with, but actually as I progressed, I found that there were clusters of definitions, and some of these groups were much larger than others, and within the group, often there'd be the same ideas expressed again and again, either in different language or at different levels of abstraction. And there were actually a lot of similarities, particularly within what I think is the main kind of cluster. And so what I tried to do, based on my review of all these definitions, is put together a very general and simple, but also fairly mainstream view on what intelligence is, and use this as my informal definition to start with. Okay? So, the first thing is that intelligence is a property of some active agent. You have something, it interacts with the world, some sort of environment or so on, and when you're talking about intelligence, you're talking about a property of this agent. And that's fairly universal across definitions. The agent has to interact with an environment. It doesn't really make sense to think of the intelligence of a system that has no external interaction. And this turns up in a lot of definitions, as you'll see as well. And it's to do with the dynamics of this interaction and what goes on there. Intelligence is a matter of degree. We often, when we're speaking, we say something is intelligent or isn't intelligent, but really it's fairly clear that it's a matter of degree. There's some things are more intelligent than others. There's some kind of scale there. Another property, which is perhaps slightly less obvious, is that the intelligence is related to the agent's success in achieving goals. It's not that the agent is just sort of drifting around and doing whatever, but there's some tangible sense of success or failure. And intelligence is to do with the agent's ability to make decisions to lead to achieving some sort of goal or so on. And this also comes through in quite a few of the definitions you'll see. And finally, the environment is not fully known to the agent. So the agent has to be adaptable. It has to learn, it has to adapt, it has to adjust itself, it has to come up with, invent new strategies, it has to be creative, it has to have all these things in order to be able to deal with the fact that it doesn't know what the environment is to start with. It doesn't know what problems it could come up against. And so it has to be able to deal with a wide range of what I call environments. They're actually a wide range of different problems and situations it may encounter during its operation. So, my informal definition then is intelligence measures an agent's ability to achieve a wide range of goals in a wide range of environments. Okay? So it's a very general ability to achieve stuff, to make decisions based on your experience in order to achieve the types of things you want to achieve. And this is I believe this captures the essence at an abstract level, a lot of the definitions that we'll see. I'll show you a sample of them in a minute. And it's also something that you can try to formalize, and I'll do that later. We can formalize what an agent is. We can formalize what goals and environments are. We can formalize what a wide range of environments are, and so on. Yes?
Why does it have to achieve goals? I mean, if it fails in its goals, is it still not intelligence?
So it's an ability on average. Okay? So if you generally fail at every problem you encounter because you're unable to make the decisions, then
it's not intelligence.
Yeah.
Is the goal part of the definition of an agent? Does an agent have to have a goal? Like
yeah, okay.
Interconnected?
So this is a sort of slightly, this is a point that trips up people. Coming from a reinforcement learning background, we use slightly unusual terminology here. And when you run into this problem of, okay, there's a few things going on. One is that our goals are actually going to be part of our environment. And usually, that makes it mathematically easier to deal with everything, because we want to consider this whole range of environments and all the different problems you might want to achieve in them, right? But, and that sort of makes sense from a reinforcement learning sort of standpoint. But actually, if you physically build a robot or something, then the robot is going to have to interpret its environment, and it's going to have its goal sort of inside itself, right? Yeah. And it's going to actually decide what constitutes success or failure and all these sorts of things. Now, you could have a model where the agent is able to have access to its own goals and define its own goals. You need to be quite careful there, because you can have things come unstuck quite easily. So you can say, well, you can get this sort of Zen Buddhist kind of situation where, well, how am I going to be really successful? I know, I'll just define my ultimate goal as doing nothing. Wow, I'm incredibly successful. So if you're able to just arbitrarily define your own goals, then you can, So when we want to measure the intelligence of an agent, what we actually need to do is we need to constrain it with some goal. So you'll be given an IQ test, or you'll be given some problem to solve, and what we want is we want you to optimize towards that goal so we can measure your performance. If we can't do that, we basically can't measure how able you are, because you could always...
But what about the intelligence of the goals? What do you mean? The goal setting, is there intelligent goals to measure intelligence and unintelligent goals to measure intelligence?
Well, we're going to consider all the goals.
Sorry.
We're going to do the whole space. And I'm going to define that a little bit more precisely soon. So it's a very, very general thing. We're not going to exclude anything, more or less. I'm going to gloss over a few of the details. I should also say that at some points here, I'm going to say things which are not quite technically true, because the full technical details get quite complicated. So I'm going to say things like probability distribution over sequences. And really, I'm talking about a lower semi-computable semi-measure defined over cylinder sets on blah, blah, blah. All right? So I just want to say that up front somewhere, that it's not that in order to get the idea across, I need to sort of gloss over a few things. And they're not hidden, they're all in the books. You can read all the technical details, but for a presentation, you just get lost in all kinds of details that don't really matter. You got a question?
I was wondering if you could do away with the word goal and just say intelligence measures an agent's ability to perform well in a wide range of environments, or does it specifically need a goal to achieve?
What does perform well? I mean, you have some environment.
It has to be designed to do something well.
Yeah, but
it isn't necessarily a goal, so it doesn't have to be a planning agent.
Sorry?
Well, when I think of the word goal, I think it has to move towards a goal using a plan.
I don't care how it gets there.
Okay.
And I'll
It's
formalize
just the
some of
goal
these
is
things as I
binary,
go
whereas
on.
this isn't.
Yeah.
All right, thanks.
Okay, so now let's have a look.
Just one more
So-
question here.
Oh, yes?
I don't want to be pedantic, but are we going to get into the definition of wide?
Yes?
Excellent.
A little bit.
Because
But if you want more, ask me and I can talk for ages about it. I can put you in the papers and everything, whatever you want. Okay? So, first of all, just get this in mind before we start looking at a few definitions. So I just want to sort of support the fact that this is not a off-the-wall definition by standard ideas of what people think intelligence is. Okay, so intelligence measures an agent's ability to achieve goals in a wide range of environments. It's big space of goals, big space environments, general sort of ability to achieve stuff. Okay, so let's have a look at some definitions from psychologists, which we use the word intelligence to mean the ability of an organism to solve problems. So you've got a few things coming out here. You've got the organism, so you've got some kind of agent, and you've got solving new problems. And so it doesn't know, presumably it doesn't know what the problems are in advance, if they're new problems, right? So it has to be able to deal with some wide range of possibilities, or some reasonably wide range of possibilities, because it doesn't know what it's going to encounter. And then, by the fact that it's got the ability to solve them, there has to be some notion of what success is in this sort of situation, right? Okay. Intelligence is part of the internal environment that shows through the interface between person and external environment as a function of cognitive task demands. And so here we see the important point that you have an agent and an environment, and it's the interface of the interaction between the two that we can actually measure the system, right, and get some idea of the dynamics of the system and hopefully the intelligence of the system. And you're seeing that we need to have an agent and environment, as I've broken up before, and so on. And you've got some sort of task demands which are cognitive in nature. So these are again the problems. The person possesses intelligence insofar as he has learned or can learn to adjust himself to his environment. So again, you've got the notion that it's a matter of degree here, because these are all, of course, definitions for people. And I'm not really so interested in definitions for people. I really want a definition for machines, right? A much more general thing. So obviously, whenever they say people, I want to sort of put agent in there, general sort of agent. And then learn to adjust themselves to the environment. So there's some notion of adaptation here to some environment, which if it has to learn and adapt to it, then it doesn't fully know what it's going to expect to start with. It may have some idea. Okay. It's a global concept that involves an individual's ability to act purposefully, think rationally, and deal effectively with the environment. So again, you've got this interaction with the environment. You've got this notion of dealing effectively, so there's some idea of success or not failure with the environment with respect to some kind of a goal here. A cluster of cognitive abilities that lead to successful adaptation to a wide range of environments. Wide range of environments. Excellent. And now here they talk about, it's a little bit different here. So this is an idea, this is an example of how my definition is a little bit more abstract than some other definitions. And they talk about a cluster of cognitive abilities. Now, I don't view intelligence as a cluster of cognitive abilities. I view it as the result of some cognitive abilities. And the result is your ability to successfully do stuff, right? And so you might have planning, you might have the ability to categorize, you might have the ability to recognize or predict or do all sorts of things. Humans may have some of these abilities. There may be cognitive abilities that humans just don't even have, that machines in the future will have. And so intelligence is not actually these cognitive abilities, it's actually the result of these abilities. See what I mean? So in some sense, my definition is a bit more abstract. Okay? But nevertheless, it's quite similar in flavour, and it's got the wide range of environments, which is exactly what I'm going for. So now we'll switch over to some AI research and definitions. Intelligent systems are expected to work and work well, so we've got some concept of success here, in many environments. So here we've got our wide range of environments, and then the property of intelligence allows them to maximize the probability of success. So there's some notion of some goal or something, some where they succeed or fail with respect to that goal. So you've got it coming out again, doing well in a broad range of tasks is empirical definition of intelligence. Great. To act appropriately in an uncertain environment, so again it doesn't know exactly what the environment is, where appropriate action is that increases the probability of success. And success is the achievement of behavioural sub-goals that support the system's ultimate goal. Similar sort of thing again. Any system that generates adaptive behaviour to meet goals in a range of environments is said to be intelligent. So hopefully you believe me now that while you may not agree with my particular definition of intelligence, at least it's not completely off base with what a lot of people are saying about this. It's an agent's ability to achieve goals in a wide range of environments. Okay, so if we have at least an informal concept of intelligence now, we've got some idea where we want to get to. We'll sort of clarify that a bit, and I'm going to clarify this more later. Now, we don't have any practical machine that actually satisfies this definition. So what are we going to do? Well, we could start trying to build a machine that can do that, and that's really hard. One possibility is to try to theoretically study the problem and say, okay, we're going to ignore computational cost, and we're going to try to come up with a theoretical machine which is intelligent. Now, a lot of people object to this. A lot of people say, oh, but if you're ignoring computational cost, you're basically throwing you're throwing out the essence of the problem. And yeah, I accept that the computational cost is obviously very, very important here. But nevertheless, prior to this work by Huta, nobody had ever actually managed to even define such a system ignoring computational cost. And maybe, and I think the answer is, to some extent we have succeeded, maybe if you do study such a system and you formally define it, you're no longer waving your hands around, you can actually prove stuff about this, you can learn something about the problem. And then once you have a theoretical machine and it meets your criteria for intelligence, you can then think about, okay, we actually have something very explicit now. We have all the equations. How can we try to approximate this in a tractable way? And I think that's possibly progress, and history will tell whether that turns out to be progress or not. But at least we've formalised it. We've actually said explicitly what we mean here. And so there's some people I'm never going to convince about this. Some people really think that if you're doing this theory stuff and you're not worrying about computable cost, then you're wasting your time. But I don't think I'll ever convince them otherwise, probably. So anyway, this is what we're going to do. We're going to ignore computational cost, and then we're going to try to see if we can come up with a theoretical solution to this problem. Okay, so we're going to begin with inductive inference. Here we have a nice sequence for you. 1, 3, 5, 7. And what comes next? 9? We have a vote for 9. I hope most of you suspect it's 9. So the question is, why do you think it's 9? One reason you might think it's 9, well, the standard sort of explanation, is that you've used a principle called Occam's razor. And you've looked at the sequence, and perhaps you recognise that there are other possible explanations for the sequence. But the simplest explanation is that you start with 1, you just add 2 each time. And the simplest explanation is consistent with what you've seen, generally seems to be the most likely thing, right? And this is the philosophical principle of Occam's razor, and you've all used it. And in fact, in intelligence tests, they expect you to use Occam's razor. They'll give you sequences, and you could invent some reason why it's some other answer, some complicated explanation. But they design it so that there is a significantly simpler explanation which will give you the quote-unquote right answer. And so even in intelligence tests, they actually expect you to use Occam's razor. And we're going to return to this later. It's not usually in the definition of intelligence, but I argue that if you really want to formalize it, you actually need it. And that's why it turns up in intelligence tests. So, the answer, what, 9? Because you've used Occam's razor. And the simplest explanation is 2n minus 1. Okay. Now, you're all wrong. The answer isn't 9. I'm sorry to tell you. The answer is actually 57. Okay. And the reason why is that it's actually generated by this sequence here. This is the generator. Okay? Now, you can't be expected to get that right. But the intelligent thing to do is to use Occam's razor. And most likely it was probably going to be this. But you're not sure. You don't actually know. And so this highlights a second important principle. And that's that there's actually an enormous space of possibilities. There's an enormous space of different explanations for things that you've seen. And you can't throw any of them out if they're consistent with what you've seen. If they're inconsistent with what you've seen, then sure, they can't be right. Because what you've seen is impossible under this hypothesis about the world. But you can't throw away ones that are consistent with what you've seen, even if they seem quite unlikely. So this is another important philosophical principle. It sounds quite obvious, but it is important. So we want to have a very wide range of possible, when we're doing inductive inference, we want to start with a very wide range of possible explanations. We don't want to throw out anything that's inconsistent with what we've seen. And we want to use Occam's razor in judging which are the most likely things given what we've seen. Okay. So the second principle I explained was the Epicurus principle of multiple explanations. And that's keep all hypotheses that are consistent with the data. And if we're really serious about all hypotheses, this should be an enormous space. Okay? But if you're keeping all the hypotheses that are consistent with the data, you've got this enormous space of possibilities, all kinds of crazy explanations. So how are you going to make sense of this? How are you going to make any useful predictions? Well, you use Occam's razor. And that among the hypotheses consistent with the data, the simplest is the most likely. Okay. And then, if you want to formalize some of this process a bit more, we come into Bayes' rule. This is the first of my equations here. And essentially what this is saying here is that the probability of some hypothesis about the world, given the data you've observed, is equal to the probability of that data given the hypothesis times the prior probability of the hypothesis, and then there's some normalizing term. So we'll just ignore this down here. And so this is useful because it's not too hard often to figure out how likely is it that I've seen something if this is actually what's really going on in the world. Okay? And if you can work this out and you have some idea of how likely this hypothesis was to start with, then you can figure out how likely your hypothesis is about the world. And so you've done inductive inference. You've gone from your data, what you've seen, to distribution now over different statements about the world. Now, the really problematic thing here, this part here often isn't too bad. One of the really problematic things is, where does this thing come from? This is the probability of some explanation of the world before you've seen any data. So how likely are different things before you've seen any data? And essentially Occam's razor tells you something about this. It argues that among all the hypotheses consistent with the data, well, you haven't seen any data, there's nothing to condition on, the simplest is the most likely. So if we want to build a good prior here, and we believe in Occam's razor, what we want to do is we want to have the prior probability of different explanations about the world in proportion to how complex they are. Simple explanations are more likely, more complex explanations are considered less likely. Okay? So, in terms of Bayes' rule, Epicurus says that the probability, this is our prior probability, should be above 0 for all h. So we're considering to start with this huge range of hypotheses, and that h belongs to some very large set. We don't want to exclude anything before we even begin. And then Occam says that the probability of the hypothesis depends on the complexity of h. So what we need to do, if we want to really formalize this, is we want to say what this very large set is, and we want to come up with some measure of the complexity of the hypotheses, right? And then we can actually formalize both of these these philosophical principles and come up with some sort of inductive learning system that does that. Okay, so what we're going to use is something called Kolmogorov complexity. And turns out that Kolmogorov complexity in this case is a little bit involved. It's described in my thesis. It takes about a page. But the intuition is pretty simple. And that's sufficient for us. Essentially, the Kolmogorov complexity of something is the length of its shortest description. And the intuition is quite simple. So let's say you have a sequence of a trillion zeros, right? A very short description of that is a trillion zeros, right? And you can describe it in terms of a computer program for I equals 1 to a trillion, print 0. And so it has a very short program. And that program is in effect a description. It's a computable description. And so if you want to describe something that's much, much more complex, say, or even a little bit more complex, something like pi, the program is quite a bit bigger to generate the infinite sequence of digits of pi. And then there are much, much more complicated things where there are only very large programs to describe them. So the intuition is that simple things are things that you can describe very compactly. They have short descriptions. Complex things only have long descriptions. They don't have short descriptions. That's your intuition. Okay? Between complexity is all to do with the description length. How short is the description of the thing? And so here we say that the Kolmogorov complexity of some, there's going to be a probability distribution over sequences, is the length of the shortest program. And so to go back to our example here, we had the sequence before, 2 to the n minus 1. This is what you all suspected using Occam's razor. It has a very short program, so it has low complexity. This here is going to have a longer program. It has higher complexity. That's the intuition. So if you believe in Occam's razor, this high complexity, low probability. Oh, sorry, low complexity, high probability, high complexity, low probability. Okay? Right. So this is the universal prior probability of an hypothesis. What we do is the distribution is, we have the length of a program, and it's computed by a universal Turing machine, which takes bits as input. And so with each bit, the probability halves, right? For the length of the program. This is why we have 2 to the power of negative. So that's just a half, and then it just multiplies up. So the intuition is that the more complex the explanation about the world is, the lower the probability, and vice versa. Okay, so that's your intuition. And then that is Occam's razor, defined for you. And we take the space of all the hypotheses here to be essentially all distributions over sequences, which is an enormous space. We actually even do it more general than that. But, yeah, I won't get into that. So, this prior respects Epicurus' rule because, well, firstly, this is an enormous space here. It's all the different distributions. Yes?
But you wouldn't expect, would you expect the sum of the probability to be 1?
So, yeah, there is some. You have to normalize a bit, and it depends how you define some things. If you use so-called prefix-free universal Turing machines, then the prefix-free property on the program lengths means that you can bound this using Kraft inequality, and then you can normalize properly, or you can do other things. So yeah. Okay. So yes, it is delta. Okay. So yeah, it respects Epicurus' rule because anything that's going to get anything has with a finite that has a computable distribution is going to be finite here, so it has some positive probability. So that's satisfied, and it formalizes Occam's razor. We've got the complexity is proportional, inversely proportional to the probability. Okay, so we've formalized. We've come up with a prior that captures Epicurus' rule and Occam's razor. Now, there's a little bit of technicality here. If you want to actually predict over sequences, we need to actually consider all the different hypotheses and then the probability of the sequence you've observed so far, and then sort of mix them all up, okay? So if you use the probability theory, this is an expected thing to do, right? You consider all the different possible explanations for what you've seen. You have to weight according to how probable they think what you've seen is and how probable you think that explanation is. If you don't follow that, don't worry about it. That's what you go. So here's our Xi symbol. It's Marcus's favorite Greek letter. And this plays an enormous role. This distribution has some incredible properties, some very, very special properties. Now, what we're going to do is we're going to try to predict sequences using this C distribution, okay? And this is called Solomonoff induction. And so what happens is we have some sequence omega, we've seen all these digits coming along, and it's coming from some distribution that we don't know. That's the whole point. We don't know what's generating the thing. We're trying to infer what that is. We're trying to learn something about the world. And so the notation here is that we have omega, that's 1 to n, so that's the digit, the first digit up to the nth digit. That's what we've observed, time n. And we're trying to predict what the next bit is in that sequence. Okay? And so the way to do that is just basic probability theory. We just take the conditional probability. Given what we observed, probability the next bit is say 0. We just take the standard probability, conditional probability stuff, right? So it's the probability of what we observed with 0, and normalized by the probability of what we observed. Simple as that. How well does this work? Turns out it works ridiculously well. Just insanely great. It is really insanely great. For any unknown computable distribution, and this can be anything. This can be quantum mechanics is actually a computable theory, right? It's Turing computable, the update equations and all these things. It includes that. Relative Newton's laws of physics, you can put this in this format. Any computable distribution over anything you observe. So this is a massive space. This is absolutely gigantic, right? And for any of these possible hypotheses about the world, you don't even know what they are to start with. The expected total error, and I won't define exactly what that means, but it's basically the deviation between, the expected deviation between if you actually knew the correct answer versus if you're using this as a predictor. And you can see it in the thesis, of course. Over the infinite length, so that's over all the predictions for the rest of infinity, it's bounded by a constant. There's a constant amount of error you're going to make, no matter what it is that's generating the distribution. And you look at this constant, that is the length of the shortest description of the actual generating mechanism. This thing is learning almost as fast as if you just told it the answer to start with. It's ridiculous. Now, if you read about this, one of the things that people complain about is the Kolmogorov complexity depends a bit on the choice of reference machine. It depends on the language you're using. But it's bounded by a constant there. And so even if you change the language around, you're just putting a constant number of bits in here, maybe 1,000 bits or something to go between different Turing machines. And so if you actually plug this into, say, a video feed, and it takes 1,000 bits more to converge, I mean, come on. This converges for anything. You just plug CNN in here and it'll start modeling the entire world that CNN sees or whatever, right?
But it's only a theoretical calculation.
The catch. The catch. It only works in theory because C is not computable. If it was computable, we'd probably be trying to predict the stock market and becoming fabulously wealthy. Yes?
Is there a problem with fractal type functions where the shortest program may actually be very short and yet the complexity of the output is actually very high?
Well,
does it misestimate the probability?
Okay, so when you say that, what you're saying is that essentially the complexity of something is not just a function of its length, but it's a function of its computation time. And that's a perfectly valid way to view complexity. And it's not the way Kolmogorov complexity views it. Kolmogorov complexity says, for example, the laws of quantum mechanics, right? You can write them down, in some sense they're quite simple, right? And so in Occam's razor sense, maybe that's a good explanation. On the other hand, actually computing what's going on in a complicated system using them is incredibly intractable, using a classical computer anyway, right? So that's fair enough. I agree with you. You may want to use different notions of simplicity than just Kolmogorov complexity. And you can quite reasonably argue that. Okay?
It's like Mandelbrot says different to a sine wave. That working out what is the function that generated it,
right,
are both very different, things, and one would take a lot more computational time.
Yes. Yeah.
Well, perhaps see the random output.
Yeah.
I mean, which is in theory very short on all the complexity, but figuring out the program is computation of energy cost.
Sure. Yep. So that's it's a perfectly reasonable perspective to take. It's an alternative perspective.
I think the trick here is that you're using something that's not computable, so it does all the computations in parallel for every possible fractal, cryptographic, what the fuck.
In a sense, it's already built in.
It is every time looking at all the implausible things, and so it's not going to take any more than the number of steps that it needs to get the definition anyway, just because it's looking at everything.
Yeah, it computes everything. And it's actually, if you are concerned about the compute time as being part of the definition of complexity, that actually kind of helps you in a way, because it means that working out the complexity of something is now bounded in time, because you're not interested in all the explanations that take forever to run. The bad news is, if you actually try formalizing a definition of complexity, like homographic complexity, with time in there, it gets a bit difficult. You run into problems. 11 complexity is one, and we're going to run into that in a second. Okay, so, catch, not computable. And this is why we're ignoring compute time, but we have this optimal predictor, okay? So, some people say, well, Solomon induction has nothing to do with reality. It's all, infinite computation, da-da-da-da. Well, if you... The approach we're taking here is that you define something in theory and then you look at how you can approximate it, right? So we've got a concrete target, how do we approximate it? And it turns out with Solomon induction that it's this ultimate prediction scheme, and if you break it in certain ways to make it a bit more tractable, you actually get a whole lot of standard statistical things coming out. So we get map estimators, MML estimation, minimum description length, maximum entropy. So one view of Solomon induction is that it's sort of a model of ideal inductive inference when you're ignoring computational cost. And then in practice, what we have to do is we have to try to approximate it. And really the only point I want to make here is that even though we're ignoring computational cost, it's not completely disconnected from the world of statistics. It's actually, you can do equations, make some simplifications, and get a whole lot of normal statistical stuff that is computable out of it, right? Okay, and if you want to know more about that, that's the reference there. And homographic complexity in general, that's pretty good. It's one of the standard references. Okay, so what we've done so far is we've come up with this perfect predictor, okay? Perfect theoretical predictor. But we want more than that. Our definition of intelligence required an agent which interacted with an environment, right? So the agent can't just sit there and observe the world and internally figure out what's going on and predict what's going on. It has to actually make actions in order to achieve some sort of goals or something. And so we need more than just prediction. We need to have this active agent. And so a standard way of doing this sort of thing in the area is called reinforcement learning. So basically we have our agent, we have our environment, the agent can perform actions that affect the environment, and then there's rewards come back from the environment, or more realistically, the agent has some sub part of it which it can't modify, which decides whether what is a reward or not. But theoretically, this is more useful, easier, nice setup to work with. And then we have these other things which are just observations. So that's just observations of what's going on that have no particular reward meaning. And this is standard setup called reinforcement learning. Okay, and so the agent's goal essentially, its internal goal, is to maximize the amount of reward it gets. Okay. Now this produces some interaction history over time. The agent performs an action, the environment returns an observation reward, the cycle continues, and so I formalize this as follows. So the A's are the actions, O's are the observations, R are the rewards, goes along over time, up to say time t, and then because I'm going to have to deal with some complicated combinations of sequences and so on, I need a little bit of notation here. So what I do is I stick these three symbols together and then index them 1 to t. So this whole sequence here is AOR, all of them up 1 to t. Okay, so that's going to help shrink down some of our equations. Okay, so we take an agent to be a probability measure over actions conditioned on the history. So basically, the agent has everything it's observed so far, all the actions it's taken, all the observations, all the rewards, and then there's some probability distribution over what its action is going to be. Okay? So this is a very general agent. If it's deterministic, only one of these things will have a probability of 1, everything else will be 0. And this is in more compact notation here, it's just the same thing. So this is a very general agent. We're not assuming it's computable. It could be working by magic, so long as it defines a distribution. It can be stochastic, because it's a distribution. So it's a very, very general class. And it's conditioned on the entire history, so we're not making any Markov assumptions or anything here. This is very, very general. And we want to keep it that way. The environment, we just essentially do the same thing, but it's the other side of the interaction. So we have a distribution over what the next observation reward are, given the entire history so far. Okay? And the agent's goal is to maximize total expected reward. And so this is the V function here. So this is the interaction between our agent pi, the environment mu, and the expected amount of reward it gets is the expectation. Okay. So this is a very, very general framework. And I want to emphasize that. You can put just about anything you can think of in here. You could have playing chess. You could, you're one player, you've got another player, the other player is the environment, your actions are moving your different pieces, you observe the moves of the other player, and maybe you get a reward for winning the game, otherwise you don't get anything. Another possibility is you might get rewards as you take pieces. If you take the opponent's queen, you get a positive reward. If you lose your queen, you get a negative reward. If you lose the whole game, you get a big negative reward. Okay? Going through a maze, answering questions, an IQ test. You have to answer the questions. You observe the test. You get rewards for doing well. Passing a Turing test, you get a reward if you pass. You have to interact with somebody on the other end. You try to figure out whether you're a machine or a human. Writing an award-winning book, anything you think of, you can put into this kind of framework. So it's very, very general. And so we have to think about what is our opponent likely to do. We have to consider the space of all the different things the opponent might do and predict what it's likely to do or not do. And so if I was playing chess against Garry Kasparov would probably make moves that were not optimal if he was playing a grandmaster. Because he knows that I'm a terrible chess player. He can make a move and assume that if that's a slightly risky move for him, I will miss some subtle reply to it and then he can crush me. Right? But he wouldn't do that move with a grandmaster because he knows the grandmaster will see what's coming up. And so how you play the game depends on who you're playing against if you really want to play optimally. Right?
If he cares about beating you quickly.
Yeah, if he wants to destroy me quickly. If he wants to be really sure to destroy me, then he may act differently. Right? Okay. But you can see that what's going on here is that you have to consider all your moves, then assuming that any of those moves are taken, you then consider what are the likely things your opponent is going to do. And then for each of those possibilities, you have to then say, well, now it's my turn, what am I going to do? And you look at the best move. And then you consider, well, what is the opponent going to do? And you have this big tree of possibilities, and you sort of mentally go through this in your head when you're playing chess. So we have maybe something like this. This is our present situation. We can take the pawn with the queen and get checked. We can lose our queen. So this step here is what we do. This next step, and this next level is what our opponent does. And then the next step is what we do. And it iterates all the way through, okay? And so we can assume, we're free to choose our own moves. So we can assume when we're choosing our own moves, we'll choose the best move, as far as we can tell. So for this step and for this step, they're our turns, we can choose our own moves. So we'd have the maximum, we take the best. When we're looking at these other steps here, we have to consider how likely it is that our opponent is going to do different things in response. Okay? And so we have to know the probability of the agent doing, our environment doing different things. And we have to consider the consequences of them. And as we go through this tree, there's certain maybe rewards as we go through. So, say going down here, lose a queen, well that's pretty bad. We take a knight, maybe, in return. So that sort of partly compensates. But it's still pretty bad. We get down to a checkmate here, and that's the ultimate reward. And so we have to optimize over this whole space of possibilities. So how do we do that? We have this big nasty equation. And this big nasty equation is really we're only one step away from the AXE agent now. So bear with me, we're getting there. This big nasty equation just says what I just said up here, that in symbols. So we have, as I said, we have our own actions. These are the A's here, and we maximize over these because we can choose our own actions. So we make the best action we can make. So that's a maximization. And then what we have to do is we have to consider, we have the sequence of our action, the environment, our action, the environment, our action, and so on and so on. So we have a maximization over our current action at time t. Then we have to take the sum over all the different things the environment can do. These are our observations, rewards. And we have to weight it according to the probability, this is the environment here, the probability that the environment actually does this particular thing. So that's the probability of the other player taking your queen when you do something silly, or the probability of the other player just ignoring that. So we have to weight all these possibilities. And so we go through this tree. Our action, we take the best action we can, we've got all the different possibilities that the agent will reply with at time t. Then we have our action at time t plus 1, our next action, then we have the environment, and so on and so on and so on. And we have to weight all these according to how likely we think the environment is to do all these different things in response to our moves. And then we have here all the different rewards. So we're actually taking an expectation of all the rewards. This is a probability, this is what we're taking expectation of. We have to have this whole tree of possibilities. Maximizing our actions, taking the expectation with respect to the distribution of the rewards for the agent on the outside. So this is really just a formalization of this. And you can see the tree structure coming here. With the alternate our move, environment, our move, environment, our move, environment. And we're trying to come up with the maximum amount of rewards. And this is our model of how the opponent behaves. Okay? So it looks pretty scary. It's actually conceptually not that strange. Now there's a big, big problem with this. In general, if we want to be able to remember our definition of intelligence as the ability to perform well in a wide range of environments. Now this performs well, this performs optimally when we know what our environment is. Right? So that's not good enough. We don't in general know what our environment is. If we know what our environment is, we can brute force compute and come up with a solution. So that's one problem, that we don't know what our environment is. The other problem is that this is, of course, very, very difficult to compute. It's an exponentially large tree, and we're taking it all the way out to infinity. But we're ignoring computational cost. We'll get back to this later. We will get back to this. So theoretically, anyway, if we ignore the computational cost of this huge tree as we look through, ideally, all possibilities in the tree, we don't know what the environment is. But we have Solomon induction. This here is actually just a prediction of what the environment is going to do, right? We have Solomon induction, which converges insanely well for anything. So what we can do is we can say, well, we don't know the true environment. How about we drop a Solomonov predictor in there, right? So we replace the true environment with C. That was Marcus Hooter's idea. And this is what we get. So it's the same equation, but now we've got a C in here. So what it's doing is we don't know exactly what the environment is going to do, but we use Solomonov induction to predict what it's going to do to all the different futures. Okay? And that is AIXC. If you manage to bear with me, that's the basic model of general superintelligence, ignoring computational cost. And you can prove that it converges to optimal behavior in any environment where this is possible for a general agent. And there are some environments where it isn't possible. So, for example, let's say you have an environment, you have two doors. They're unmarked. You go through one door, you can never come back, well, both doors, you can never come back through either of them. One takes you to heaven, one takes you to hell. What do? You have to go through one of them. No matter how smart you are, you can't solve this problem. You just have to guess, right? So you can't actually have the optimal behavior in this environment unless you know in advance which door you have to take, because there's nothing you can do to find out about it, right? So we have to have this sort of caveat here where it's in any environment where this is possible for a general agent. And it turns out there are many environments where this is possible. So one of the things I did in my thesis was to try to spell out, there are other optimality results, by the way. There's Pareto optimality, or balanced Pareto optimality, there's a whole bunch of different things. So one of the things I tried to do in my thesis is to spell out more exactly.
So
Yes?
that's saying that it's not like a binary thing, like you live or you die. You can actually do repeatable measures on your environment so that you can have a learn. Is that's not what you're saying, or that's what you're saying?
If you have one chance in one world and you have to go through the door,
Yeah. So you're
just have
saying
to
that it
guess.
has to kind of be, you have to be able to do repeatable measures, so you can actually got a learning part.
Yeah, kind of. And it gets a little bit subtle. So it's basically, by repeatable, it's technically ergodic.
Not repeat, yeah.
It's an ergodic environment. And so if your environment is ergodic, it sort of basically means whatever mistakes you make, you can do something that sort of gets you back to before you made mistakes. So that's an important concept here. So, and you can see that this sort of, it looks like it basically satisfies our informal definition of intelligence. We want to be able to achieve a wide range of goals in a wide range of environments. And this converges to optimal in any place where it's possible for a general agent. So it satisfies our definition of intelligence, in theory. This is not computable. So I wanted to sort of flesh this out a bit. I won't tell you details of how I did this. But basically, it's in the chapter. I formally define what all these different things are. We have Markov chains, ergodic MDPs. So this is the ergodic thing you were sort of alluding to there. We've got Markov chains, Bernoulli schemes, classification problems, bandit problems, blah 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 blah, computable sequence prediction, function. There's a whole bunch of stuff, and this is a taxonomy. So as you go down, this becomes more and more specific. Some of the things up the top here are just too general, but basically below some level here, everything in this space, it's possible under the definitions I give for a general agent to converge to optimal, and we know AIC converges in any of these situations. And these are whole classes of problems. These are not specific problems. These are entire domains of problems. So I would argue then, if you accept the definition of intelligence, the ability to perform well in a wide range of environments, AIC performs optimal in all these environments. So it satisfies that definition of intelligence. Okay. Now, the computability. This is the big problem. It's not computable. And it's bad for two reasons, essentially. One, this is just not computable at all. It's pretty bad. And the other thing is that this here is exponential. It's that whole tree I drew earlier on, right? It grows exponentially. So you've got two problems to deal with. One is you need to replace the Lomonoff induction with something that's actually a real predictor. Two, you've got an exponentially large search. Now, people try to solve these kinds of problems. People try to deal with these search spaces when they make chess playing programs and Go playing programs and all kinds of stuff like this, right? They try to deal with this kind of problem. And people try to build predictors as well. So, what can we do? Well, there's a guy, Joel Vaness, and he has a background in making chess playing programs and Go playing programs. He's been quite successful at this. And he's now being supervised by Marcus Winter, among others, in Australia. And he did the fairly obvious thing. He took the expecting max tree, which is this thing here, and he used multicolored tree search, like they use in Go. And he took the Solomonoff predictor, and he replaced it with particular choice was context tree weighting. And you have to throw in a complexity weighting as well for the complexity of the model, because we want this Occam's razor to come in, right? And you can rewrite this equation in a slightly different way, and then if you actually rewrite what this is, it almost looks identical. It's
so
just
Monte Carlo tree search means you don't do everything, but you do a random selection of different outcomes, and you think you hope that's going to be a sufficient estimate.
Yes. Yes, and you take all these samples through your tree, and you then try to put confidence intervals at different points in the tree of how good or bad things are, and you then adjust which parts you're going to look at intelligently and so on. And so there's a whole bunch of work has been going into there in chess playing program, the Go playing program, and so on, to try to intelligently search through all these possibilities. And so we can use existing technology, and we can come up with this Monte Carlo AIC. This is the reference here, the paper. And you get something that actually does things. So you can do simple prediction problems. Well, that's not really surprising. It's got a predictor built into it. It can learn to play tic-tac-toe. It can learn to play paper, scissors, rock. It can learn to find its way through mazes where it can only see locally. So I can't see the whole maze, and it's in some corridor, and it doesn't know, it has to actually walk down the corridor and mentally count how far it's gone in order to be able to know which decision to make at some point. It doesn't actually know its absolute location.
How does it know that it's making progress in maze solving? I mean, presumably it's not.
Well, it's a reinforcement learning environment, so when it gets to the end of the maze, it gets a reward, and then it has to try to solve it again.
Multiple mazes.
Yeah, it gets to multiple experiences. Yeah, so it's the same with tic-tac-toe. It gets to play the game a lot of times. And then so do. Various types of tiger games. So these are games where you're in front of a door and you can listen, and you can then hear a roar of the tiger sometimes, and it's probabilistic. So you're not once you hear it, you're not completely sure where it came from, but it gives you a bit of information, and so you have to figure out how long to wait and how many times to listen before you make the decision of which door to go through so you don't get eaten by the tiger. So these are slightly subtle sorts of problems where you have to sort of optimize multiple different things. And computer games. It can learn to play Pac-Man. Yes?
So I want to come back to a question that was asked earlier and a comment you made. This is really for deterministic systems.
No.
And that comes back to the stock market comment you made.
It's not for deterministic systems. Okay. These are all probability distributions. So paper, scissors, rock is not deterministic. You can have prediction problems where some stochastic sequence with a bias in there or whatever.
Okay.
Yep. It's all generalized over distributions.
Got it.
Is it not that all these environments have kind of a Markov property?
No, these particular ones?
Yeah.
No, some of them are POMDPs. They're partially observable.
Okay.
Yeah, so this is a POMDP. So it's not assuming Markov. And the general model for AIC doesn't make any assumptions about these things. It's the whole history of conditions. Yep.
So presumably, a system like this could never, if you were to ask it how it came to its decision, unlike the Grand Master, who said, why did you come up with such and such solution? You could explain it logically and rationally, but a system like this could never do that.
Well, it doesn't. Yeah, it doesn't have any language, so that's a problem.
No, I mean,
but you can,
if it did have language.
Well, you can internally look at it, the model. You can internally say, okay, here's the tree that you looked at. These are the probabilities you think different things are going to happen, say in the chess example. And so you think that the other player is really good, and so they won't miss this obvious move. And so this is the combination of moves that leads to a good outcome. So you can inspect the model. Yep.
What about games that don't have yes or no answers, have shapes of game, brain,
Sure.
like poker and things like that?
Sure. So you can,
Well,
the reward is not necessarily binary. So that's one thing.
But it's a probabilistic distribution.
Sounds like a good way to get yourself.
Well, that's no problem. Probabilistic distribution is no problem here. It optimizes the average reward. And so at sample, it plays many games of poker, and it tries to optimize
You
it.
can teach it poker, use that to fund your research.
Yeah. Right.
Question from Michael?
Have you put them against each other to see if they get into infinite regress? And if it knew that its opponent was the same algorithm in Prisoner's Dilemma, would it be smart enough to cooperate, knowing that its opponent will do the same thing?
So I didn't actually do this work, so I don't actually know if he's tried that. He may have. With the Prisoner's Dilemma, there's been previous work with AIC, and you can show that it solves it in expected sorts of ways and stuff. Okay. You've seen AIC in action. It's the world premiere. Joel was kind enough to send me a copy for this presentation. Okay, so only a small community is concentrated on general intelligence. Nobody has tried to make a thinking machine and then teach it chess. That's the key thing. The bottom line is we haven't really made that much progress. Quote from Marvin Minsky. Now, the thing here is that this Monte Carlo AIC learns to play all these games. We don't have 10 different Monte Carlo AICs that we play all the different games with. You can make up a game of this sort of complexity. Just invent one and give it to it. Come back the next morning and it's learned to play your game. Right? So it's quite general. It has a number of other very interesting properties. One of them is that it's so-called embarrassingly parallel. Because it's using Monte Carlo tree search, you can farm this out across tons of servers and break up the tree search, right? So if you had a supercomputer or you had access to Google's cluster or something like this, you could farm this out pretty efficiently and it would do massive searches over big spaces, right? So it's quite easy to make this code work in parallel. That's currently going on at the moment. Oh, I should also say about teaching you to play chess. They're currently trying to get to play checkers. And then if they can get checkers working, they're going to try chess. So I don't know if Marvin Minsky would then approve of that, but at least that's what they're doing. They're actually making a system and trying to teach it checkers, teach it chess. Yes?
So it's like a baby, it's like learning that.
Mm-hmm. It starts with just a general compressor. It has no model of the world.
Now it's getting onto checkers.
Mm-hmm. Yep. And you can then save the model it has. You can like save its brain in a sense and fire it up. So yeah, it's embarrassingly parallel. You can parallelize across massive hardware. In the future, when there's zillion core CPUs, it's going to work quite a lot better. Much more exciting.
Time and storm bot and everything.
Yeah. It's an anytime algorithm. And what that means is that you can run it for a fixed amount of time. You've got 3 seconds. And it will then return the best answer it's managed to come up with in 3 seconds. And you see this in Go playing or chess playing algorithms. It has this property. And that's a really nice property if you want to scale the system up. And you can tell it that it has to run within a time constraint. And it just works the best it can within that constraint. If you give it more time, obviously it can do more searching. It can work better.
Sorry, with the anytime algorithm with Go, how does it determine, like, with the time, the number of trees as opposed to the depth?
It just adaptively builds them as it goes, and then you just cut it off. You say time's up, and it just returns the best answer it has. The point is, it returns a sensible answer given time constraints, as opposed to some algorithms. You've got to run the algorithm for 1.5 minutes before it returns an answer. If you need an answer in half a minute, you haven't got an answer. Okay? And another cool thing is that it's using this Monte Carlo, it's using this context tree weighting. And you can play around with the compressor. The context tree weighting, there's limited things it can do. It can't build hierarchies of sequences and all kinds of certain types of things like that. You can play around with the compressor and add other things in there. You can put logical rules in there. So you can say something about your environment. You can put a few logical rules in. You just plug it straight in, and suddenly it starts working a lot better because now there's a huge space of possibilities that it doesn't have to worry about.
So who's the you there? Is that the programmer or is that the intelligence itself?
No, it would be the programmer in this case. And so some of the work they're doing at the moment is to enhance the compressor. You can throw all kinds of machine learning algorithms in there to find patterns and all kinds of stuff to make the system learn better, right? It's more general there. So some people freaked out when they saw this. Because some people are very worried about super intelligent machines destroying the world and doing all sorts of things in the future. You don't need to worry about this. Firstly, Joel is quite aware of these problems, and he's interested in the work by the Singularity Institute and all these sorts of things. He knows about these problems and he considers them to be real problems. So he's not. And the other thing is that while it seems not impressive, if you really think about it, it's kind of actually, it's very general, but it's sort of like ant level of intelligence. It finds its way around a maze eating pills, right? And it plays papers as rock and things like this. So at the moment, there's no danger of this. And the models are well known, they're well understood, the compressors are well understood. There's nothing too crazy going on here. So there's no need to panic. It would be, it's sort of as light years away from being able to, say, understand its own source code. I mean, there's no chance of an ant writing a self-improving AI anytime soon. So you don't need to worry about this, at least not for a few decades anyway. And in fact, as impressive as this is, I don't think this is the way that's going to drive AI forwards.
Can I just, I just want to check my intuitions, not gone off down the wrong road. It wouldn't be very hard, presumably, if you've got sort of an array of these things running, to bolt on a higher level that gives it directives like understand your own source code, or do anything that's dodgy.
How do you say? How do
well,
you,
I mean, you know,
how do you code understand your own?
Well, no,
source
okay, work out what the ARC algorithm is, or or anything we don't want an AI to do.
Right.
It wouldn't be very hard to have a high level that.
Yeah.
This is basically just a powerful.
Yeah. Well, you can do that in a much simpler way. Just have a search over all programs and keep running them and divide it up in parallel and 11 search type argument. And you can run evolution. You can do lots of things which, in theory, can lead to these things. But in practice, it's so computably intractable, it just doesn't happen. And so I think this falls into this category. We would need much smarter compressors. It's just using a compressor from text compression. It's a text compressor with search strapped on the front of it. That's basically what it is. And so it's not going to take over.
So it's essentially then, like, would you say that intelligence is dimensionality reduction, ultimately?
No. We'll talk about that later. I think it's ability to achieve a wide range of goals environments. And things like dimensionality reduction are very important parts of being able to do that. But it doesn't necessarily capture the whole concept. Okay?
That's why I asked the question about agent in the beginning.
But what about moral inferences?
Yeah.
For instance, is there a set of rules which create another dimension that say it can interpret and say this is an action I shouldn't take, or this is an action I should wait and do more often?
Right. There's no reason you couldn't put that in. At the moment, it's just trying to play back. So there's no.
That's just a reward, isn't it?
Yeah. So you can, in theory, try to put things in. Yeah. So maybe we'll talk about some of these later because we're actually going through an hour and a half so far. Okay. So I actually don't think this is going to really drive stuff forwards really soon. I think there's actually another area which is going to get some big mileage out of. So that's my scary story for later. Okay, can we formalize this? I'll try to go through this reasonably quickly. Basically, when we've defined AIC, we've actually defined all the parts that we need. We have all the machinery that we need to formalize what this is. Because we've defined an agent, we've defined succeed goals, we've defined a wide range of environments. We've got all the bits. And so you just basically assemble all the pieces together from the AIC machinery. It naturally comes together that you have a definition of intelligence. The only thing that's missing is that this says nothing about Occam's razor. And when we want to measure the general ability to achieve goals in a wide range of environments, we need some way of weighting these environments. And essentially that's what Occam's razor tells us. It says that a priori simpler environments are more likely. And so if we want to test the agent in such a way that using Occam's razor makes sense, we need to weight the environments according to the complexity. And so if you put it all together, we know what our agents are, we've got our wide range of environments here, which are all our computable distributions. We've got our Occam's razor here, that's the complexity of the environment or weighting. And then we've got the expected success of the agent in this environment. And we just consider all possible environments. So this is the wide range of environments. This here is the success. The goal is sort of implicit within the environment, and then we just take the whole lot. We just look at the expected performance across the whole space environment. So it contains everything. Is it intelligence? Well, I've just argued a second right before that this formalizes the definition I have. And so if you accept the informal definition I have, this is a formal characterization of it. Each of the symbols corresponds to part of the informal definition plus Occam's razor. So I think you can argue that in a formal and a very, very, very general sense, because that's what I want. I want a very general concept of intelligence here. It can apply to machines and anything super intelligent in the future or whatever. It formalizes a lot of these ideas about intelligence that we see from psychology and AI research and so on. It's very general. It says nothing about the internal workings of the agent. The agent can use magic to come up with its distribution over its actions. That's fine. We don't care. So we're not making any assumptions about what's going on inside. It doesn't have to be computable. In fact, AIC isn't computable, and we can talk about the intelligence of AIC. So it's very, very general there. Agents with high universal intelligence are very powerful. It turns out that, in a sense, this intelligence measure is the dual of AIC. AIC is the perfect agent. This is the measure that has the same structure where AIC is the maximal element. Okay? And so we know, theoretically then, that if something has a very high universal intelligence, it's going to be optimal in this massive space of environments and so on. So having a very high universal intelligence theoretically really means something in terms of the power. Right? And it's also practically meaningful. if you had a system that was able to achieve a wide range of goals in a wide range of environments and converge to optimal, do all these things, then that's really quite a significant practical thing, right? So it's not meaningless in reality if you have a high measure. It's not anthropocentric. This is a big problem with the Turing test. You have to convince some judges that you're human, right? And so a key part of passing the Turing test is being human-like. You have to make spelling mistakes. You have to not be able to multiply two 20-digit numbers in under a second, right? You have to do all these sorts of things. So it's really a test of humanness. And the idea is that if you're sufficiently human-like, well, intelligence must have come along with it. But I would suspect that actually by the time you can pass a Turing test, you're already superhuman intelligence. Because you're able to fake being something of a completely different nature so convincingly that humans can't tell the difference. This says nothing about humanity. It's all defined in formal mathematics. It just comes from computation. And finally, it's formally defined. Even if you don't like my definition of intelligence, you don't agree with my equation, at least I've said exactly what I mean. There isn't any ambiguity in here. I'm not saying, intelligence is the ability to have conscious interaction in a creative way or something like this, where I'm really just moving the problem of defining intelligence into all these other words that I haven't defined. I've actually given you an equation, and I've said precisely what all these parts are. So even if you disagree with me, you should disagree with me in a very specific way, because I've said exactly what I mean, okay? Yes?
So just on that point, how do you actually measure that intelligence though? So if you do have a machine with the AI XR, how do you assess that intelligence compared to a dog or a person?
Well, how do you practically apply the intelligence measure?
Yeah.
Okay, so it has this, again, we're working in theory, it's not a computable measure. Okay, so again, what we have to do is we have to approximate in practice. And I want to mention a few efforts to do that in a second. And finally, I would say that, because the measure considers the space of all environments which are computable, have computable distributions, right? It's in a massive, massive space. So if somebody comes up to me and says, your definition of intelligence, it's not the right definition because you haven't taken account of, insert your favorite thing, consciousness, creativity, or whatever. Okay, so let's take creativity. I would then answer, well, is creativity useful for being able to succeed in some environments? Now, there are some problems that require creativity to be able to, that helps you being creative. And if the answer is yes, then creativity is already being measured by this. Because you're using your creativity to be able to work better in these environments that require creativity in order to solve problems. So it's already taken care of it. What about consciousness? If consciousness is important, my question is, does it help you do stuff, consciousness? If it does, it's already being measured. If it's not being measured, it means that in no computable distribution over any possible universe can consciousness help you do anything, right? In which case, I don't really care. Well, in terms of intelligence, I don't care. Philosophically, I might care about consciousness or something like that. But it's not actually helping any system achieve anything. And that's what I'm worried about here. Okay, so can this be made practical? Less work has been done on this, but there are a few things going on. It's just sort of starting this area, I guess. I had some intention to do some things in this area, but I just haven't got around to it. I've been distracted. So Matt Mahoney has been essentially sampling from C. What he does is he generates random Turing machines with some time bound on them and gets them to spit out a whole lot of stuff. And the stuff that comes out has essentially a kind of universal distribution. And then he uses it to benchmark compressors. And as you might expect, the really good compressors that work well on all the benchmarks work well against a universal distribution as well. This guy here, this was back in 2000, it was a while ago. He had some similar ideas about intelligence, and what he did is he put together a definition of intelligence using Kolmogorov complexity, and then he approximated it using something called Legg complexity, which takes the time into account. So it's not just description length, it's time, like what you were asking about earlier. And then it's computable. And he then managed to come up with sequence. He only did sequences. He didn't do full interaction systems like I'm arguing for. So it's a bit more limited in that sense. And sure enough, he came up with sequences, and you had to then predict what's coming next. And unlike usually in an intelligence test, you get all these different sequences you have to predict, and some are harder than others. Where do they come from? Well, people think that this seems to be a bit harder than that. Here, we actually have numbers. We can say this sequence has complexity 9, right? This sequence has complexity 14. And sure enough, as this number goes up, it gets much harder to predict the sequences. And what he did is he took a whole bunch of these, gave them to a lot of students, and gave them IQ tests. And sure enough, the IQ test and their ability to deal with complexity correlated. It's not that surprising, really. So this is actually a computable, but only in the sequence prediction sort of domain, right? And finally, Ben Goertzel is about to publish a paper where he takes this universal intelligence stuff and then tries to approximate it in different ways and do various things. It's not published yet. He sent it to me on one of the guys who provided comments and so on for his paper, so I can't share that yet. But he's doing some work on that as well. So there are some things happening here, but it's still quite immature. Okay, now, do I think that all this universal theoretical stuff is going to drive AI in the future? I think it's good. I think it's a big improvement. But I suspect that some of the key things are actually going to come from neuroscience. And if you look at the Monte Carlo AIC, really, if you want to make that work well, a lot of it comes down to building better compressors. So it's better at predicting what's going to, it has a better model of what's happening in the future. And so while you've now decomposed the problem into Monte Carlo tree search and having very good compressors, you still haven't, that's a beginning, but there's still a lot of the problem to be solved. How do you deal with all sorts of complex sequences and stuff? You need to build very, very powerful compressors to do these things. So it hasn't fully solved the problem. In order to solve the problem from there, there's an enormous amount of research to be done with compressors and actually really doing all the modeling of what's going on all over this. So I suspect that where we're going to get a lot of things from, a lot of mileage from, is theoretical neuroscience. And this is the reason why I haven't actually been working on complexity type things recently. And I've come to London to work at the Gatsby unit at University College London. And the Gatsby unit is an interesting place because they do theoretical and computational neuroscience and machine learning. So they're actually working at the interface of two different areas. One is all the theoretical machine learning stuff from artificial intelligence, and the other side is the computational theoretical neuroscience. And they're finding the points at which these things are crossing over. And I think that's really interesting, and I think there's a lot of interesting things happening there. And so I'm arguing that the brain is not a black box. Usually I don't have such a gory picture of a brain, but it's Halloween. You got the cerebellum here, you got cerebellum down here, you got cerebral cortex, a bit of brainstem. Right. So when we look at a brain and you start looking at some theoretical neuroscience, you actually start to see a basic architecture for an artificial intelligence. It's really neat. So I'm going to try to explain in the minutes that remain a little bit of this. So this is the cerebral cortex. So this is this part up here. Not the stuff under here. Well, there's a whole bunch of stuff underneath this. So there's actually a whole bunch of, so this is sort of the outside view of the brain. Your brainstem coming up here, and there's a whole bunch of stuff underneath this, subcortical. And that's important too. But we'll start off with this here. This is a very interesting system. One of the first interesting things about it is that it's basically a sheet. And it's got all these folds in it because it's being crumpled up to fit inside your skull. It's actually about the size of a dinner napkin, right? And it's such a useful thing. The brain seems to have had to evolutionary scrunch it all up to fit inside your skull because it's of such value. It wants to get more and more of it in there, right? And this sheet acts as sort of like a computer to the brain. And it has a fairly consistent structure. It's got, depending how you count, 6 to 12 layers. And it's pretty similar across the whole from the back to the front of the brain, up and down. It's pretty similar. You find similar kinds of neurons and similar layers right across the whole thing. Okay. Now, the way it's split up is you have, basically, this is the back of your brain, this is the front of your brain. The back side here, there's something called the central sulcus down the middle here, which is a kind of a valley. Now, this whole blue side, the back side here, is the perception side. So basically what that does is you have information coming in from the world, and it processes that information. So here we've got area 17, that's the primary visual cortex. So you've got, from your eyes, you go down to optic nerve, you go to something called LGN, then it gets projected up to here. And here, you've basically just got a map of what you're seeing, okay? So this is where the visual information comes in. 41 here is the primary auditory, so your sound is coming in here. And then along here, you've got touch and proprioception, so it's like angles of your joints and stuff like that. So this is all your touch stuff, this is sound, this is vision. And then what happens is that at each of the, say in vision, it's a little bit more complicated. You've actually got multiple pathways and sort of stuff going on. But basically, what happens is that you get different areas going up, and it goes from very, very simple, like a map of what you're seeing, to finding more and more abstract features of the world. And so it builds a hierarchy of abstraction from the most basic features like edges, orientations, moving edges, areas of light and dark and so on. And it builds up more and more abstract features until you get up to this lighter area here, this is association cortex, where it represents things like Bill Clinton, right? And you can find neurons up here which will respond seemingly just to Bill Clinton. You can have a picture with a whole bunch of people, and the neuron fires when there's Bill Clinton there. Bill Clinton can be a cartoon, not a real picture. He can be young, he can be old, all sorts of different things. And so up here you have representations which are very, very abstract. Here, it's not so abstract. Same thing goes on in sound, same thing goes on motor. On this side here, it's the lowest level sort of touch stuff. As you move away from it, it's much more abstract things to do with what you're perceiving about from touch. Right? Now, if we go over the other side, we've got the same basic idea going on, but now it's an executive system, it's the action system. So along here, we have all your ability to drive muscles. So this is all the muscle driving to move your fingers and speak and do all these sorts of things. And then as we move away from this, it becomes more and more abstract. So it starts having plans of action and then whole sequences of action, all the way up to sort of long-term conceptual thinking about things, right? And so you've got this beautiful architecture, you've got this hierarchy from low-level perception all the way up to more abstract sort of perception. And then on the other side, you've got the executive side, the action side of things, from very low-level things up to very, very abstract things.
Down the central fissure, you've got the representation of the body.
Yes, yes.
Do they match up?
Yes, they do. So you have actually a sort of a linear map of your body. I can't remember exactly. You got your hands are down here or up here, or your face and your tongue and everything. And then on the other side, it matches up. And what happens is that if you actually look at the connectivity, you've got this mirror image. They actually connect at about the same level. And then this holds up the hierarchy as well. So you've got an area up here, Broca's area, which is to do with the generation of sentences and meaning in sentences. And then you've got a Wernicke's area, which is the corresponding part over here, which is the recognition of the meaning of sentences. So you've got the generation side and you've got the recognition side. And if you damage one of these, you can lose a specific ability. So if you damage this area, you can lose the ability to recognize the meaning of sentences, but you can still construct meaningful sentences because you've got the generation side, and vice versa. And not surprisingly, these two areas connect up with each other. This area doesn't connect down to this area. It wouldn't make sense. So what we have is we can basically take this and we can remap it out into some hierarchy. So we have all your sensors here, you have the information coming in here, it becomes more and more abstract as you go up, and also the sensors become integrated. So you have things up here which represent things to do with touch and sound. And then on the other side, you've got the same thing, but you've got the executive side of things, right? And that drives your actions and so on. And so you've got muscle firings down here to do things, all the way up to long-term conceptual planning. And what you find is that these actually interact with each other on similar levels of abstraction. Okay? Yep.
How many neurons take you from like the bottom of that structure to the top?
I don't know. It's in some cases they can estimate it for vision because you can figure out how long it takes, and it's actually very few.
I would say that you can probably do it less than 10 hops from the bottom to the top.
10 hops, yeah. It's something that's from vision type things.
Yeah. So it's hand wavy because there are always a few shortcuts. You said it's 10 neurons from the bottom to the top. Is that what you said?
Up the hierarchy, yeah.
But it's not an exact number by any means.
Yeah.
You can get nice little loops and deviations.
Mm-hmm. Basically, you can present an image down here and you can see how fast it recognizes Bill Clinton up here. And you know how fast information propagates through neurons, so you can calculate basically. Right, I need to get moving, so the questions might have to wait for the pop. Okay, so this is quite an interesting structure. It looks like something you might actually design if you're building an AI. Now, there's actually more going on. So I was talking, under here you've got all this subcortical stuff. Now this here is basically just a model of what's going on in the world, and the information doesn't just go up, by the way, it comes back down. So you can actually see something and be expecting at a conceptual level to see something and it can interact with each other. And the same here, the information goes up and down because it has very, very similar properties. Okay, so underneath this we've got another system down here which has all kinds of things in it, and some of the things that it does is essentially like a reinforcement learning kind of system, which I was talking about before. And so what happens is at an abstract level you could say, okay, we have an environment, the information comes up here, it gets processed from raw representation up to very abstract conceptual representation. On the other side we have our executive process which generates the actions back out to an environment. We have our low-level stuff, we have very conceptual stuff out here. And then we have a reward system on top of this, which sort of is the goals and directs and modulates the whole thing. Okay. Now, how does this, I'll begin with this system. How does this system work? What do we know about it? Turns out we've actually learned a lot about it. We're making a lot of progress at the moment about this. The last 5 years, huge amount of progress. And it's really amazing what we're discovering. We're discovering that the brain is using a whole bunch of algorithms that we already knew about. Algorithms we already discovered in machine learning. Of course, it's not using some of the algorithms, like it's not going to use a least squared algorithm, which is really optimal. You need a big matrix, you invert it. It's pretty hard to do in neural computation. It works really well. So we actually have better algorithms than what the brain is using in some senses, though they have higher time complexity. Anyway. But yeah, standard algorithms that we know about, the brain is actually using these algorithms. It's really incredible. So one algorithm is temporal difference learning. Now I was going to put the equation up, but I figured we'd probably have fatigue by this point. So the idea is actually very, very simple. What you do is you remember the V function we had before. That's the expected reward. Okay. So what you do is you have a model in your system. What is the expected reward in this state of the world? What's the expected reward? What do I expect in the future? How good is this? And then what happens is that you experience what comes next. And what you do is you compare what you expected with what actually happened. You look at the difference, and then you update your model based on the difference. So if you expected to get a big high out of something and it turned out to be not so great, you're going to update your model so in the future in that situation you're not going to expect as much as you previously did. And you incrementally update your model. And you can adapt the other way as well. Now if we go looking in the brain, this is in the dopaminergic systems. Dopamine it seems to be a key thing in this whole process. This is the dopaminergic neurons in VTA, ventral. Yep. And so what happens? Okay, to start with, this is the beginning. We have a stimulus. This is the old stuff. I'm showing you like some pretty original things. There's actually much better recordings, but it's nice going back to some of the more original stuff. So okay, we show a stimulus at this point. The monkey goes, oh, okay. And then we give it a reward at this point, and just after the reward there's a big jump in the activity of these neurons. And so what's happened is that it didn't expect anything great to happen, but all of a sudden something did. And so there's a difference between its expectation and what actually happened. There's a big positive difference. I didn't expect that anything cool was going to happen after I saw this. Wow, that's really good. I didn't expect chocolate bars to taste so good. I ate the chocolate bar. Wow, that's really good. So you update your model so that next time you eat a chocolate bar, you see a chocolate bar, you expect it's going to be tasty, right? And so what happens after a while is that you show the stimulus, then there's an increase here because it's expecting the future to have a certain amount of reward. When you actually give it the chocolate bar, well, it's actually juice, that's what they usually use. Monkeys love juice. There's no spike anymore, right? Because it's updated its model. There's no error. There's no difference. You see the algorithm working? And then you can do this. You can do the same thing. You can. Is that going off the edge? No. So you can show the. You can show the stimulus. Then you get a spike here. If you present the stimulus, nothing happens because it's as expected. If you don't give it the reward, suddenly these drop down. And that's sort of like a negative, right? It's a negative prediction. And so it then has to update its model the other way. So this is the old stuff, and there's been a ton of stuff following this, and it's basically what we're finding is the brain is using a whole bunch of algorithms we already know about. It's really incredible. So there's tons of stuff. I'm not an expert in it. I'm just going to show you a few bits of it. Okay, so this is a bit problematic representing a negative sign in a spiking neural network, right? So this is a bit difficult. Well, turns out that there's a part called the habenula, which is computing the negative of this. And that makes it much easier. So if you were actually designing the system in a neural net, you'd probably put this in yourself. Does the brain use model-based or model-free reinforcement learning? This is a big split within the area. Some methods, okay, I'm not going to go into it. Some methods have an internal model of the world, and then they can do much more powerful things, but it's a lot more computationally expensive. Other methods are sort of model-free, are much more computationally cheap, but they're more limited in what they can do. So you have a trade-off between the power of what you're able to do and how much computation you have to do. Now, what does the brain do? Some people in the field, in machine learning do these, some people do these. What does the brain do? It does both. It does both, and it switches and knows when to switch. When it can use the cheap system, it uses the cheap system. When that's not good enough, it switches over to the more expensive system. And you can actually identify which parts are computing these different systems. And if you have a mouse or whatever that's damaged in one of these parts, you can show this performance reverts back to the theoretical performance of these types of algorithms when it doesn't have the ability to switch anymore. So it's pretty clever. It's using both types that we've actually developed long before we knew this was going on in the brain. It already figured that out, and why don't use both types and just intelligently switch. Another trick that we use in practice is we have pseudo rewards. So for informative cues and things like that, we don't know if it's going to associate with any reward in the future, but it could be useful. So as a general heuristic, we might want to internally reward the system for doing that. Turns out the brain's using that trick too. It's stealing all our tricks.
Now you're trying to steal it.
How does it deal with complex temporal sequences? So the way we do this in reinforcement learning is we use something called hierarchical reinforcement learning. And I'm not going to explain it all, but this is a typical sort of hierarchical reinforcement learning model. It's got all the different bits in there. This is the error of the rewards. It's the temporal difference, so-called actor-critic model, blah, blah, blah. I haven't got time to explain it, but these are all the parts of the brain that seem to be doing all these bits. Now, I presented this to a group of neuroscientists. Some of them are quite expert in this, including neuroscientists from other parts of UCL and some visitors from America who work in this stuff. And you know what they told me? I gave an hour-long talk just on this. It's not my work. I was summarizing the work of these guys here. And what they kept saying was, they didn't say this is wrong. They said, Aha. But we know over here or wherever, we know more than this. The brain is not just doing this, but it also does this and this and this and this and this and this. So this is actually just a simplified model of what we know. And these aren't boxes where we don't know what's going on in it. These are algorithms we already knew about. We already coded these. You can download code that does these types of hierarchical reinforcement learning. We're actually starting to understand the reinforcement learning that's going on in the brain. It's really quite amazing. And this is progressing very quickly. There's all kinds of new stuff. There's these genetically modified mice that can they can switch off different parts of the system and precisely identify the functional roles, and it's pretty neat stuff. Now, I've asked a number of neuroscientists in the area, will we have a good understanding of RL system in the brain by 2020, right? The answer I get is typically, oh, we should understand it before then. In fact, we have a pretty good outline already, right? This part of the brain really is a lot of progress going on here. They're really starting to get a grip on it, and they expect well within 10 years they should have it. By 2020 we should have really, it'll be in textbooks, pretty standard. Right, so that's the reinforcement learning part. Now, the big problem in reinforcement learning is that if you just have a robot and it's in the world and it can move any arm in any direction and all these things, it's a gigantic space of possibilities. And it's also looking at this pixel view of the world, and it's this enormous thing. So what you need to be able to do is you need to be able to abstract the world out in order to make it manageable to deal with the complexity. So what you need is you need some sort of, say, hierarchical abstract representation of the world. Firstly for your actions, and secondly for your perceptions, in order to make it all, hey, what's the brain doing? It appears to be doing just this. And if you look at the connections, you've got this dopaminergic and all this stuff in the basal ganglia connecting up into the cortex, which provides this higher function. So we're actually starting to see something like an AI design here. And this is what the brain is doing. So, do we have anything that does this type of processing? Well, we've actually been making quite a lot of progress in doing that kind of thing. I don't know if we're going to have enough progress in the next 10 years to be able to replicate brain-type behavior, but we are making a lot of progress. And I think one of the really promising areas, a lot of the work is done by a previous director of the Gatsby unit where I'm at the moment, Jeffrey Hinton, with something called restricted Boltzmann machines. And they have all kinds of properties that are actually very much like this hierarchical system we see in the brain. So you can train deep networks. Previously in neural nets, you had a lot of problems training deep networks. We needed to figure out how to do it. These algorithms, you can train deep networks, the hierarchical networks, and you see increasing abstraction as you go up the layers, just like we see in cortex. It has a local learning rule, meaning that when you adjust the weights in the system, you don't need to know about stuff all over the system. You just need to have a look at information passing through where you are. And that's exactly what you have with synapses. They can't do some global fancy computation. They have to count spikes passing by where they are, more or less, right? So you need a local learning rule. These have local learning rules. It's a generative model. It can both recognize and generate behavior. And that's exactly what we see in this cortical system, right? We've got the recognition system, the generation system. It's able to do multiple constraint satisfaction and filling in. So it can observe a whole bunch of things, and then you can ask it to generate something which is none of the things it's seen, but it's a bit like some combination of them. It's very, very flexible in this way. It can be made temporal, it learns sequences in time. It can even be implemented with a spiky neural network. So we don't usually do this because it's more efficient to do it in a slightly different way. But it can actually be implemented in a model that's more like real brains. So I'm not saying it's the same as cortex. Cortex is a kind of complicated thing, and this is, but it appears to be the same general class of algorithms. That's what I would argue. And it has many of the similar properties. And if we're trying to build an AI, it's not necessarily that we have to exactly replicate cortex, is that we need something that provides that type of function to our system. And this seems to provide a similar type function. So, I'm really running out of time here, but I'm almost there. There's a couple of videos, which, do I show the videos now? Maybe I can show you the videos later, because we're sort of running out of time. But
you're going to get onto the Halloween story as well?
Yeah, the Halloween story.
We should wind up in a few minutes.
Yep, okay. Okay, so I have actual videos, I can show you afterwards, where the system is generating. You can get it to imagine things, and you can actually see it imagining things. which is really neat. You can get it to learn walking. And so you see the system walking, and then it observes walking, and then it can generate it. And it'll walk around your screen in a natural way. And then you can get it to move between different styles of walking. So it can move between walking sexy to walking in like a John Wayne cowboy style. And then you can ask it to do both at the same time, and it actually comes up with some combination of them. It's a very, very powerful generative model. And it's the same type of system which also works for recognition. You can get it to recognize characters, do image recognition, all kinds of different things. So I can show you those videos afterwards. So I'll just get them over. Okay, so I'm going to try and wrap up in about a minute. So if we can build human level intelligence, I think we can almost certainly scale it up to beyond human level intelligence once we understand how to do it. A machine that has well above human level intelligence will probably be able to understand its own design and design even more powerful machines. That seems fairly reasonable. We have no idea how to deal with this. We really are in the dark here. Now there's an institute, Singularity Institute for Artificial Intelligence, studying this problem. One of their core goals is to develop something called friendly AI, which has a very high level of safety for humanity, no matter how super intelligent it becomes. Now, they don't really know how to do that. I mean, we can see it looks like there's probably going to be some problems or at least some serious risks here. We don't know how this is going to play out. This is quite risky. So, this is my Halloween scenario for you all. I think in the early 2020s we should have petaflop desktops. That is not radical. You can build a desktop machine today with a few of the latest high-end graphics cards and get 10 teraflops, right? Of SGM performance at least. In 10 years we should be at petaflops. In fact, even if we slow down our current rate of progress, we'd be at 10 petaflops. So this is somewhat conservative.
So a petaflop is 1,000 times as fast as a teraflop.
Yeah, so this is 1 and then 15 zeros after it, calculations is equal. Okay? So what? Are we going to have powerful algorithms for deep belief networks? I think we're already getting there. I haven't shown you the videos, you can see them afterwards. They do some pretty fancy stuff. And it looks like it's in the right sort of space of algorithms. It has the right sort of properties, right? And remember I said this is a key thing, to reduce down the space of possibilities of reinforcement learning to make it work well. So I'll put a question mark here. I don't know how it's going to progress. Are we going to be at a point in the early 2020s where we can basically provide the same type of functionality that the Cortex provides for an AI system? We've made a lot of progress in the last 10 years. So I think it looks like we're heading in that direction. Furthermore, if you've got desktop machines with a petaflop, you can make much bigger networks, but more importantly, you can test a lot more ideas. So all the students, and I'm talking about desktop machines, because all your grad student stuff get desktop machines. They don't get supercomputers. These are the guys who actually drive a lot of the progress forwards. They can run 1,000 times as many experiments. Well, they can run 100 times as many experiments on 100 things that are 100 times as big. And so that really speeds up research. Because you don't have to wait a week to see the results anymore. You can run 10 different variations in a matter of an hour. So you can try all kinds of things. So I think this is actually going to speed up this quite a lot. And we've already made, just in the last 5 years, there's been a lot of progress here. So I think it's possible, but I've got a question mark on there, possible that we'll have some really good temporal deep belief networks in the next 10 years. Possible. Brain reinforcement learning, that's going to be nailed. Really. We're making great progress there. The people I speak to expect it's going to be pretty well understood. And we even know better algorithms than the ones that the brain appears to be using, because we can just take a matrix and invert it, and the brain finds that pretty hard. So we can actually just brute force a lot of these things and do them in really good ways, right? So we can probably do it better than what the brain does. And this is the early 2020s. And this, I think, is the basic architecture for an AI. You've got the performance to do it, you've got the powerful algorithms to generate the abstractions, and you've got the underlying reinforcement that drives the whole thing. Now, I think a consequence of this is there'll be many groups in the early 2020s working on brain-like AGI architecture. That's artificial general intelligence. I think it's just a natural consequence of these things. If any of these groups has any significant success, they're going to be trying these things out on supercomputers pretty fast.
It's inevitable, right? And there should be exaflop supercomputers. So this is one with 18 zeros after it. And this is a conservative prediction. If you look at the supercomputer guys and what they're predicting, and say a top500.org, they're predicting an exaflop by 2019. This is what I think is going to happen, right? We're already at 2 petaflops. 10 petaflops is coming in a year, and just it's like 6 months after that is 20 petaflops. And IBM is already talking to groups about how to build the first exaflop machine. They're already discussing it with them, based on the 20 petaflop number, right? So this is the idea that we're going to be here by the early 2020s. That's actually arriving late, okay? So I think that this is very reasonable. This is very reasonable. I mean, if these things are true, then this is very reasonable. This is certainly very reasonable. That is very reasonable. This is a question mark. Will we figure out the algorithms to get them really powerful? I don't know. I suspect we might. But we're not going to have a practical theory of friendly AI. Now, I've spoken to a bunch of people, including Michael Vassar, the president of Singularity Institute. None of them that I've ever spoken to think that they will have a practical theory of friendly artificial intelligence in about 10 years' time. No way. When I talk to them, they say, well, we're kind of it's going to take longer than that. It's not going to be 2020s before things start getting crazy. I'm arguing here, we're starting to understand, I'm not saying we understand, quote unquote, how the brain works, because there will be a lot of things we won't understand how the brain works. But when we look at the brain, we're actually getting an architecture for the system. We know all these different bits, how they connect up, the basic algorithms that are being used, and in some cases quite explicitly the algorithms that are being used. So we actually have a blueprint for building an artificial general intelligence, and it's emerging quite quickly. And we're going to have the computer power to drive the thing. So that's my Halloween scenario. That in the early 2020s, we're going to have the hardware, we're going to have the exaflop supercomputers, we're going to possibly have the deep belief network. This is the questionable bit. This is the bit that could ruin the whole thing. Are we going to get a lot more? This is a hot area at the moment, by the way. A lot of people going into this. We just had a big workshop with all the top people in the world at the Gatsby unit. A lot of things happening here. This list looks like it's going to be solved well before then. So if this all takes off, we're going to have people with brain-like AI architectures plugging their systems into exaflop supercomputers, and we have no idea how to deal with consequences. And these systems to start with, maybe they're not that dangerous. Maybe they're not going to take over the world or do anything crazy. But they're starting to converge on the types of algorithms that we really should be worried about. But we don't know what they're going to do. And I will leave it there.
You can't stop there. You've got us all on 10.
Yeah, so what do we do about this?
You're going to develop researches from number 2 to number 5 to number 6, is that right?
What can you do about this? You can't slow down this sort of thing. I mean, this is a massive global effort, right?
Going to make the research on friendly AI more attractive.
I don't think you can really speed it up much. It's really hard. When I say that they're not going to develop this is not a criticism of their ability or their intent or anything like this. It's really, really hard. We have no idea how to solve this problem. I don't know if we can really speed it up.
Is the question simple as AI is going to make it easier to solve, or is it going to make it harder?
I don't know. Let's talk about this in pub. I mean, really, if you have alternatives to my Halloween scenario, then tell the world about it.